In this video, we're going to do a hypothesis test that is dealing with qualitative variables rather than quantitative variables. So we're not going to be looking at the population mean. We're not going to look at the population standard deviation. What we're going to do is, in fact, it's kind of like population proportion, where you have like the percentage of people in your group, except we're generalizing that to where you have a qualitative variable with, say, 3 or 4 or 5 different possible values or categories, and we're trying to look at the percentages in each one of those categories. Now, before I go into the details, I want to point out the example down here because I think it'll really help clarify what's going on. It says, a certain candy you like to eat comes in a bag with a mix of different colors. You would like to know if the colors are equally distributed or if some occur more than others. You take a sample and you find out how many of each color there are, and then we're trying to test whether, based on this sample, whether they really do randomly make them equal in color or if they make some colors more often than others. Right? So you might be interested in that in terms of the candy, or maybe something a little bit more serious. What if we wanted to analyze whether prisons were putting people away disproportionately based on their race, let's say? What you could then do is you could look at the population and how it breaks down by race, what percentage are this, what percentage are that, and so on. Then you look at the prisons and you say, okay, what percentage are this, what percentage are that, and so on. You match them up here. And then the question is, does the prison population match the general population? And if it doesn't, we need to investigate and see why are people in different races becoming incarcerated at a higher rate. And so, I mean, pretty big jump there from talking about candy colors to, prison and racial inequality. But this is the type of hypothesis test you would use to analyze a situation like that. So the idea is, when you have a variable that has different values and you have one scenario where you have these percentages of how they break down and you want to compare whether it matches that or not, that's called the goodness of fit test. You are matching a specified distribution, and by distribution we just mean percentage in each group using a sample. So you take a sample and you're trying to see whether or not, based on this sample, do things seem to line up well with the distribution? Is that distribution a good fit? Right? Is it a good fit based on the data we have? That's why it's called the goodness of fit test. Now, for our null and alternative hypotheses, this is where it's going to change compared to something we've seen before. So in the past, we always had that this thing was equal, the P was equal to this, or mu is equal to this, or sigma is equal to this. Always equals here. In the goodness of fit test, it's the only one that we've had so far that's not that. And what it's just going to say is the data does fit the distribution. So that would be if everything is normal and nice. If the two things match, that's our H0. And then H1 is the data does not fit the distribution. And the thing is that this is technically your H0 and H1 for every single goodness of fit test problem. You don't have to have like a left-tailed or right-tailed, two-tailed, changing up slightly and so on. You are literally always saying either it matches the distribution or it does not match the distribution. Those are our two tests here. Now, when we're going to do our test here, we're going to do something called chi-squared. We've seen it a couple times before. And in this case, if you wanted to actually calculate the chi-squared by hand, which again, we're going to have our calculators do that for us. But if you wanted to, it would be this formula here, where the OI is going to be the observed number in each group. So in terms of our data down here, the observed for red is 23, the observed for yellow is 20, the observed for brown is 26, and so on. However, the E This is going to be the expected number in each group. And you might say, well, wait a second, I don't know that. How am I supposed to know what the expected number in each group are going to be? And that's what we need to figure out how to do that. So what you're going to have to do is you're going to take the EI is going to be the sample size times FI, where FI is the relative frequency in the given distribution. So what do I mean by that? Let's say that N is 100 and we guess a distribution of 35%, 25%, 40%. So there's going to be three categories, whatever it is we're talking about. We'll call them A, B, and C for now. I'm predicting there's 35% going to be in group A, 25% in group B, 40% in group C. So what I want to do is I just take my 100 and multiply it by each one of these percentages and get an expected count of 35, 25, and 40. You might say, I'll just take the numbers there, right? But what if instead my N was 200? If you do 200 times 35%, you get 70, and then 50, and then 80. So in general, you just take your sample size and you multiply by each of the percentages that you are assuming is what your distribution is going to be, and those become your expected counts. And this is something you're going to have to actually calculate, but thankfully it's not too bad here. So let's go ahead and do that for our example problem down here. So we are trying to see whether things are equally distributed. So if they're equally distributed, and there's 4 categories, then what does that mean? That means each category is going to be 25%. Now again, if it wasn't equally distributed, then they'd give you a percent for each category and you'd multiply them separately. But thankfully, we have just 25% for each here. Now, the only other question then is, what's my sample size? So for that, you have to actually add things up here to get your total sample size. So we had 23 plus 20 plus 26 plus 25. And I'm getting a sample size of 94. And now if I take that and multiply it by 0.25, I get 23.5 here. So my expected counts for each category is going to be 23.5. And you don't really want to try to round to a whole number. Thankfully, this one just ended at 23.5, but we might have rounded it if it went on for a long time. Like if it went to 5 decimals, we probably don't need that many. But you don't want to just round to a whole number. That might make things too much. So those are our expected counts. We also have the observed values there. So let's go ahead now and see how we can get our p-value from our calculator. Keep in mind, this is a goodness of fit test. So let me pull up the calculator here. How we do tests, we go to stat, go over to tests. This time we have to scroll down for a while. And we get to where it says chi-squared GOF test, chi-squared goodness of fit test. If I hit enter there, and you see it's asking us for lists. It wants a list with the expected value and a list with the observed value. So let's go back over to our data here and make sure we have that copied down. So we have the observed and the expected here, 23, 20, 26, 25, and then for the expected, 23.5 and all. And I'm going to go ahead and quit out of this. I'm going to go back into stat, hit edit. Let me put the data in the list here. So the observed 23, 20, 26, 25, and the expected 23.5, 23.5, 23.5, and 23.5. So you put in all your data for the observed and the expected, and then we just make sure we put our observed in L1 and our expected in L2, and let's double check that that's what they wanted. So stat, go to test. This time I went up arrow, chi-squared GOF. Observed is in L1, expected is in L2. Then it asks for degree of freedom. So if we want to find the degree of freedom here, in the past, our degrees of freedom was n minus 1. And you might say, oh, well, my sample size is 94, so degrees of freedom 93. That is actually not going to be correct. I did warn you before that we were going to have different degrees of freedom in different problems. And for the chi-square goodness of fit test, your degrees of freedom is the number of categories minus 1. So it's not going to be the sample size minus 1, it's the number of categories minus 1. So since I have 1, 2, 3, 4 categories, my degrees of freedom is going to be 3. I'll go ahead and hit 3 there. And then hit calculate. And you see we get p-value of 0.82 and then say 7. So 0.827 here. That is my p-value. And what that means is an 82.7% chance that if they were equally distributed usually, that we get a sample like this. And you can see my samples, they are generally quite close to the 23.5 they're supposed to be. I mean, they're not perfectly equal, but they are pretty close here. And that's going to happen when you take samples. In fact, it's going to happen 80% plus of the time, or it's going to be a little bit off. So that's not an issue here. So that means it is good. So that does not mean that we can say that for sure they're equally distributed. All we can do is say the following is that there is not enough evidence to show that the colors are not equally distributed. If we were to go back through with different data here, just so we can see where it can work out not so nice, let's say something that it was really not very even. Let's say there were 40 red, let's say 20 yellow, let's say 10 brown, and I want to keep a 94 sample size. So let's see here, 40, 60, 70, that's a 24. So let's go back and change our observed counts to those 4 numbers, and let's see what the p-value is in this case. So 40, 20, 10, 24. I have to edit my first list to 40, 20, 10, and then 24. And let's go and do our test a second time now. Still list 1, list 2, degrees of freedom 3. And this time, look at my p-value there, 1.80, E negative 4. Right? E negative 4 means it's a really small chance of it happening. That means 0.00018, so on. And so in that case, we would reject it. So 0.0018. So the second p-value is 1.8 E minus 4, and that means you put 3 zeros in front of the 1.8. That is way less than the alpha here. So then in that case, there is enough evidence to show the colors are not equally distributed. Okay, so I this time I kind of doubled up on the example, gave you one where you rejected the H0 and one where you did not reject the H0. I think it's good to make sure you can handle both cases here. But this one does require a little bit more work on your part to have to calculate the E values, the expected values, the expected counts. But otherwise, your calculator is still doing the majority of the work for you. And so this is how we get our conclusion for the goodness of fit test.